According to the Standard Model of Cosmology, about 13.8 billion years ago, the universe began with an event known as the Big Bang. In its earliest moments, the universe was a hot, dense soup of energy and particles. As it expanded, it cooled rapidly, allowing the first subatomic particles to form. These particles eventually combined to create hydrogen and helium atoms during what's called the era of recombination, about 380,000 years after the Big Bang. This was when the universe started to become transparent. Fast forward to around 100 to 200 million years later, and the cosmic dark ages came to an end as the first stars, known as population 3 stars, began to ignite. These massive, short-lived stars lit up the universe, marking the start of the era of reionization. As the first stars formed, gravity began to pull matter together, giving rise to the earliest galaxies. These young galaxies were clumps of stars, gas, and dark matter, slowly assembling into larger structures. By about 1 billion years after the Big Bang, the first fully formed galaxies dotted the cosmos, continuing to merge and evolve into the vast, complex systems we observe today. However, we are beginning to find fully formed, mature galaxies existing within the first 500 million years of the Big Bang. Earlier this year, the James Webb Space Telescope, JWST, discovered a galaxy called Glass Z13, formed just 300 million years after the Big Bang. Webb also found another galaxy candidate called Glass Z11, which formed 500 million years after the Big Bang. Not just that, the telescope has just discovered a galaxy that defies galaxy formation models, and it has been joined by ALMA, the Atacama Large Millimeter Array, to spot a fully formed galaxy, a Milky Way doppelganger, at the beginning of time. But how is that possible? Evidence from observation shows that the Milky Way reached its maximum size approximately 11 billion years ago, which means it took our galaxy around 2 to 3 billion years after the Big Bang to form much of its structure. So what is a fully formed spiral galaxy doing so early in the universe? Welcome to uncharted territory. This is your space. The early universe was a chaotic, unpredictable place where galaxies were expected to be messy and clumped together. But what if we've been underestimating its complexity? Enter Rebels 25, a galaxy discovered by ALMA that has turned everything we thought we knew about galaxy formation on its head. Astronomers were stunned to find that this distant galaxy, which formed just 700 million years after the Big Bang, looks surprisingly like our own Milky Way. It's a massive, disk-like galaxy with hints of spiral arms and even a central bar. This discovery has astronomers scratching their heads and asking, how could a galaxy so orderly exist when the universe was still in its infancy? Further observations of this galaxy revealed that it's not just any ordinary early galaxy, it's the most distant strongly rotating disk galaxy ever found. To confirm these findings, astronomers took a closer look with ALMA. The high-resolution data not only confirmed that Rebels 25 has a rotating disk but also hinted at other advanced features, like a central elongated bar and possibly the beginnings of spiral arms. These characteristics are more in line with mature galaxies like our Milky Way rather than one born so close to the Big Bang. So where does this leave our cosmology? Well, the discovery of Rebels 25 is shaking up our understanding of the early universe. It suggests that galaxies may have formed and evolved much faster than we previously thought, leaving scientists with exciting new mysteries to explore about the birth and growth of galaxies in the cosmos. What's even more intriguing is that Rebels 25 isn't alone. The JWST has found that a third of early galaxies may have been spirals. Meanwhile, the Webb telescope has also made the crisis in cosmology worse. Here's how: our universe is expanding, and the rate at which it is expanding is called the Hubble constant. This is a fundamental parameter for understanding the universe and its ultimate fate. To put it simply, imagine the universe inflating like a big balloon. The Hubble constant is the number that tells us how fast the balloon is inflating. Now, scientists have been trying to measure this number using various methods. The main ways of doing that are: 1. Distance indicators. Imagine you're trying to figure out how fast a car is moving, but it's too far away to see its speedometer. Instead, you look at how quickly it's getting closer to you. Similarly, scientists look at objects in space like certain types of exploding stars called supernovae. These are like cosmic pinpoints in space, and they tell us how fast they're moving away from us, thereby indicating the expansion rate of the universe. 2. Cosmic afterglow. Another way is to look back in time to the very beginning of the universe, like rewinding a movie. Enter the cosmic microwave background, CMB, the remnant radiation from the Big Bang dating back to when the universe was about 380,000 years old. By examining this afterglow, we can calculate the Hubble constant. The problem is, when scientists use these two methods separately, they get different results for the Hubble constant. Using distance indicators, we get a Hubble constant of 74 km per second per megaparsec. When we use the CMB, we get a Hubble constant of 67.4 km per second per megaparsec. This is called the Hubble tension, and scientists have been at their wits' end trying to figure out why these methods don't agree. To make matters worse, new measurements from the JWST reveal fresh evidence that the Hubble tension isn't going anywhere soon. With the powerful Webb telescope, astronomers have captured a striking image of a distant supernova located in a galaxy that appears stretched and distorted. This gravitationally lensed supernova, nicknamed Supernova Hope, isn't just remarkable for its aesthetic value but of great scientific significance. The supernova exploded around 10.3 billion years ago when the universe was roughly 3.5 billion years old. Yes, that's how long the light from the explosion has traveled to reach the JWST. The discovery of this supernova began when scientists noticed three mysterious points of light in a JWST image of a distant galaxy cluster called G165. Surprisingly, these points were absent from previous Hubble Space Telescope images of the same cluster taken in 2015. Initial analysis confirmed that the unusual points of light were indeed the result of a rare stellar explosion. The team then checked the supernova for the rate of the expansion of the universe. According to NASA, the team reported the value for the Hubble constant as 75.4 km per second per megaparsec. And that is a big problem because, despite existing in the early universe, the value of the Hubble constant delivered by the observations of Supernova Hope seems to correspond with measurements of other standard candles in the local universe, while simultaneously disagreeing with measurements of other objects in the early universe. That not only confirms the Hubble tension, aka the crisis in cosmology, but worsens it. However, another group of scientists has found a different result. In a paper submitted to the Astrophysical Journal University of Chicago cosmologist Wendy Friedman and her colleagues analyzed new data taken by the Webb telescope. They made measurements of 10 nearby galaxies that provide a foundation for the measurement of the universe's expansion rate. To cross-check their results, they used three independent methods. The first method uses a type of star known as a Cepheid variable, which gets brighter and dimmer in a way that we can predict. The second method, known as the tip of the red giant branch, uses the fact that red giants shine up to a certain brightness and then stop getting brighter. The third and newest method employs a type of star called carbon stars, which have a consistent brightness and color when seen in the near-infrared spectrum of light. Fun fact, the Webb telescope is particularly designed to observe the universe in near-infrared and mid-infrared light. In each case, the values were within the margin of error for the value given by the CMB method of 67.4 km per second per megaparsec. The Cepheid variables, however, were not cooperating. From them, the team arrived at a value of 72.04 km per second per megaparsec, which is not in agreement with the other measurements. But when taken together, the four methods give an average value of 69.96 km per second per megaparsec. Further observations with the Webb telescope of galaxies containing standard candles like supernovae will be invaluable for confirming the results from these 10 galaxies. So, does this mean that the crisis in cosmology is finally over? The Hubble constant, as measured by all methods, falls within the bounds of estimations for most astronomical calculations. So perhaps there is no tension after all. However, more observations are needed to back this research.